ഓ അങ്ങനെയാണോ? ഓക്കെ, അപ്പം ഞാൻ അങ്ങോട്ട് പോവാം. എനിക്കത് കഴിഞ്ഞിട്ട് ഇങ്ങോട്ട് വരും. അപ്പോൾ അവിടെ കൺക്ലൂഡ് ചെയ്യാൻ ഒന്ന് ശ്രദ്ധിക്കണം, കാരണം മാർട്ടിൻ മിലാനിക്കിന്റെ ടോക്ക് ഞാൻ കേൾക്കണം.
Portion is there.
So one colleague of mine asked if this will be available later for viewing.
Yeah, I don't know that part, but it is recorded inbuilt. Maybe later on they will decide to put it in the online.
Yes, sir. It is available in YouTube also.
Yeah, it is parallelly available in YouTube.
Yeah. Thank you.
So recorded video will be available in YouTube. Not parallel session. Recorded video will be available in YouTube.
Great.
The question is how long it will be available. That's what he is asking, whether it will be available in the future.
How long, sir?
So it will be available in the future.
Yeah, okay.
Okay, very good. Thank you. I assume you can hear me okay?
Yeah, I will include.
Good morning, one and all. Now, for this session, the speaker is Martin Milanik. So, may I introduce the chair of this session, Professor T. Tamish Shelvam. He is a CSIR Emeritus Scientist in the Department of Mathematics of Manonmaniam Sundaranar University, Tirunelveli, Tamil Nadu. On behalf of ICNTDM, RSET, and each one over here, I welcome you, sir, to chair this session.
Thank you.
Sir.
Yeah, good morning to one and all. I am indeed happy to be part of this international conference. This is the first invited talk. This is by Professor Martin Milanik. Because it is only 30 minutes of time, just I would like to be very brief. Professor Martin Milanik received his PhD in operations research from Rutgers University in the year 2007. After a postdoctoral position at Bielefeld University, he joined the University of Primorska, Koper, Slovenia, where he is currently a professor of mathematics at Faculty of Mathematics, Natural Sciences, and Information Technologies. And he is also a research counselor at IAM. His research interests and focus are on structural and algorithmic aspects in graphs as well as hypergraphs. More specifically, he has been concentrating on domination sets and independent sets in graphs as well as hypergraphs in the aspect of algorithms. He has written over 70 papers, but the very beautiful fact is with over 90 co-authors, about a dozen of which are related to strong clicks in graphs. In 2007, he was awarded Zuas recognition, the Slovenian National Award for Important Achievements in Science. Also, he is a recipient of a travel grant from Fields Institute. So I am happy to invite Martin Milanik to talk about recent results and open problems on CIS graphs. Martin Milanik, please.
Thank you very much. Thank you for this introduction, and thank you, of course, for the invitation. It's a great pleasure and honor to be able to participate at this wonderful event, even though online. So let us start. In this talk, I would like to present several results with several co-authors who are all listed here. Liliana Alcon, Andre Boros, Nina Chiarelli, Ted Dobson, Vladimir Gurvic, Marisa Gutierrez, Ademir Hudurovic, Berenice Martinez Barona, Jerome Monod, Peter Mulšić, and Gabriel Verre. Of course, I will also mention works by other authors and cite them appropriately. So to make sure that we are all on the same page, we will be talking here only about finite, simple, and undirected graphs, which will be denoted by G. And a clique in a graph is a set of pairwise adjacent vertices, while a stable set is a set of pairwise non-adjacent vertices. Stable sets are often called independent sets, or in the algebraic combinatorics literature, they are called co-cliques. We will say that a clique is maximal if it is not contained in any larger clique. So it does not have to be of maximum size. It's enough that it is inclusion maximal. And similarly for stable sets, but also an important definition is that a clique will be strong if it intersects all inclusion maximal stable sets. So a clique is strong if it intersects all maximal stable sets. And very analogous definitions can be also made for stable sets. A stable set is maximal if it is not contained in any larger stable set, and strong if it intersects all inclusion maximal cliques, so all maximal cliques. Later in the talk, we will also use the standard notation for the clique number and the stability number. The clique number is denoted by omega of G and is the maximum size of a clique in the graph. And the stability number is denoted by alpha of G and is the maximum size of a stable set in the graph. For example, here we have a graph with 6 vertices in which this clique of blue vertices is a strong clique. Why? Because it intersects every maximal stable set. As soon as you include a vertex not in the blue clique into a stable set, you have to make it maximal, and so you have to add one more blue vertex. On the other hand, here we have in the same graph a 2-vertex red clique, which is maximal, but it is not strong because there is a maximal stable set in the graph, which is disjoint from the clique. And for the same reason, this maximal stable set is not strong because there is a maximal clique disjoint from it. The main concept of interest for this talk is the concept of CIS graphs, as the title suggested. A graph is said to be CIS if every maximal clique intersects every maximal stable set, or equivalently, if every maximal clique is strong, or equivalently, if every maximal stable set is strong. You see that the acronym CIS comes from the definition. Every maximal clique intersects every maximal stable set, CIS. And the graph we have just seen on the previous slide is not CIS because there is a disjoint pair of a maximal clique and a maximal stable set. So the first question which comes to mind, of course, is are there any CIS graphs at all? And let's have a look at some examples. Just to warm up, here are 2 very structured and simple families of CIS graphs, complete graphs and complete bipartite graphs. They are so highly structured that it's very easy to verify that all maximal cliques and all maximal stable sets intersect. Also, here is a concrete example which is not from those families. It's a 12-vertex graph with vertices numbered from 0 to 9 and also AB. And in the table on the right, we see that we have all the maximal cliques of the graph listed and all the maximal stable sets. And in the corresponding entry, we have the intersection. And indeed, the intersection is always non-empty. Of course, it can only consist of one vertex. A clique and a stable set can never intersect in more than one vertex, because here we have all pairwise adjacent vertices and all pairwise non-adjacent. This is an example taken from the chapter by Andrade, Boros, and Gurvic, which is a really nice survey on CIS graphs published 2 years ago. Well, there is more than these examples that we've seen. Here are 3 more structured families of CIS graphs. First, the line graphs of balanced complete bipartite graphs, which are the graphs as the one depicted here. This is the 4x4 example, but this grid could be arbitrarily large. So we have a n by n grid. Every row is a clique, every column is a clique. These graphs are CIS. The second family of CIS graphs is given by graphs in which every maximal clique is simplicial, meaning that it consists of a vertex and all its neighbors, like This is the case, for example, for the graph depicted here in the middle. It has 5 maximal clicks, these triangles, and each of them consists of a vertex and all its neighbors. And it's an easy exercise to verify that every such simplicial click is in fact strong. It intersects all maximal stable sets. Then there is also the family of cographs, which are equivalent to graphs without an induced 4-vertex path. These graphs are defined recursively as graphs, and here is an example, that can be decomposed into copies of one vertex graph by iteratively taking the components of the graph, or first taking the complement and then taking the components. So here you see, if we take the complement of the graph, then it would become disconnected. The top vertices would form one component, the bottom vertices would form another component. And we could iterate this procedure and decompose the graph entirely. This family generalizes the complete graphs and the complete biverted graphs, and all such graphs are CIS. What else can we say about CIS graphs? Well, if a graph is CIS, then its complement is definitely CIS, because the definition is completely symmetric in this respect. When we go to the complement, the maximal clicks are mapped to the maximal stable sets and vice versa. But perhaps more interestingly, the class of CIS graphs is closed under substitution. So we can build large CIS graphs from existing ones with the following operation. We take 2 graphs, G and H, and we fix a vertex of G. We can construct a new graph, which is called the graph obtained by substituting H for V into G. By deleting the vertex V, we assume that G and H are vertex disjoint. We delete V and replace it with H. And then we put all the edges between vertices of H and the neighbors of V in G. And it turns out that the so obtained graph is CIS if and only if both H and G are CIS graphs. So if they are both CIS, in particular, the new graph is also CIS. We can construct many CIS graphs this way, arbitrarily large CIS graphs. Okay, I have not yet said anything about motivation and where does this notion come from. So why would we be interested in such graphs? So if we try to understand where this notion came from, the study of CIS graphs can be actually traced back to the work of Grillet in 1960s. He characterized partially ordered sets in which each maximal chain intersects each maximal anti-chain. And if you think about the associated graph where 2 vertices are related, are adjacent, if and only if they are different and related in the poset, then you see that maximal chains will correspond precisely to maximal clicks. Maximal anti-chains will correspond precisely to maximal stable sets. So in some sense, the study of CIS graphs can be seen as a generalization of this particular question of on posets, which was studied already in the 60s by Grillet. Now, this acronym CIS was suggested only much later, actually by Andrade, Borges, and Gurbic in 2018. The corresponding research report was already published in 2006. One more application beside the poset comes from the fact that if you generalize the concept of CIS graphs to something called CIS D graphs, I will maybe mention something about this at the end of the talk, then those structures have applications in combinatorial game theory. And it's possible that understanding those structures could actually be reduced to understanding the CIS graphs modulo a conjecture, which is still open. I will perhaps mention this later. So there is some motivation, and I must say, I find these graphs, CIS graphs, very interesting and challenging to understand. So I would like to convince you that they are indeed interesting in this talk. Well, let's first see how complicated, how ugly they can be. Since this is a conference about both number theory and discrete mathematics, I think it's appropriate to present a construction of CIS graphs which is based on numbers. So let's have a look. Let's pick 2 pairs of positive integers, a1, b1 and a2, b2, such that their products are co-prime. The greatest common divisor is 1 of a1, b1 and a2, b2. Then we can construct arbitrarily large CIS graphs from such 4 numbers. How? We take any integer n, positive integer n, which is divisible by the product of the 4 numbers, for example, the product itself, and we place that many vertices equidistantly around the circle. Then we connect 2 vertices by an edge if their distance along the circle is either divisible by a1 but not by a1, b1, or is divisible by A2, but not by A2, B2. Well, this is just the definition. Let's have a look at an example. The first interesting case, the one which is not obtainable by substitution, is the case when the first two integers are both equal to 2 and the other two are both equal to 3. Then 2 by 2 and 3 by 3 do not have any, are co-prime. The greatest common divisor is 1. The product of these four numbers is 36. And what are the distances? Well, first we take multiples of 2, which are not multiples of 4. That means 2, 6, 10, 14, 18. No, it's enough to go to half of the number of vertices because of the symmetry of the circle. We can go on one side or on the other. Notice that we skipped 4, 8, 12, and 16, multiples of 4. And there is another generator of distances. These are the multiples of 3, which are not multiples of 3 by 3. 3, 6, 12, and 15. We skip 9 and 18, but we take all of these. And if you draw such a graph, you obtain this picture. So this is a 36 vertex graph. And you notice, for example, that if you take the top vertex and the bottom vertex on this picture, then they are a distance 18 on the circle, so they are adjacent. But if you take the top vertex and the vertex which is next to the bottom one, they're a distance 17 on the circle, and they are not adjacent because 17 is not in the union of these two sets. And this graph is a CIS graph. And we can get arbitrarily large CIS graphs with that construction. Well, so we can get quite complicated, but these are quite nice examples because they are symmetric. We can get quite large and complicated CIS graphs. On the other hand, we do not understand yet which graphs are CIS. And one possible difficulty for this, one possible reason for the difficulty is that this class of graphs is not closed under vertex deletion. For example, here is a small 5 vertex CIS graph in which every maximal click is simplicial. But if we delete a vertex of degree 2, we obtain the 4 vertex path, which is not CIS. The middle two vertices form a maximal click that is disjoint from the leaves of the path, which form a maximal stable set. And not only that, not only the class is not hereditary, it is not contained in any non-trivial hereditary graph class, meaning that every graph can be embedded as an induced subgraph into a CIS graph. With this simple construction, you take your favorite graph G, as ugly as you want it to be, and for every maximal click of the graph, you introduce a new vertex and make it adjacent precisely to the vertices of that click. The new graph, you do this for all maximal clicks, the new graph will be CIS because now every maximal click will be simplicial. So these are some possible reasons why it is not easy to understand CIS graphs. Usually when we do have the property of being closed under vertex deletion, or at least that something is excluded, that can be helpful for understanding the structure, but here we cannot count on that. In fact, no good characterization or recognition algorithm for the CIS property is known, and I believe this is the main question in the area. In fact, recognizing CIS graph, so you're given a graph, you want to test, is it CIS or not? This decision problem is believed to be COMP complete by Zhang. In fact, conjectured also to be COMP complete by Zverovic and Zverovic. But interestingly, Andrade, Boros, and Gurvic conjectured that the problem might actually be polynomial time solvable with some complicated decomposition algorithm that might exist. For example, the class of perfect graphs, we will say more about it later, is also recognizable in polynomial time through a complicated decomposition theorem. So this is an open question, and you see that conjectured answers were even going in opposite directions. So I believe it's a very interesting question. Now, what are some necessary conditions for the graph to be CIS? Let's have a look at one simple condition which is necessary. To understand it, we will need to look at the family of such graphs. So we have a clique of size k, a stable set of size k, same size, and the perfect matching between them. Such a graph is called the k-comb. K is at least 2. So this would be a 4-comb. And if k is equal to 2, we just get a 4-vertex path. Now, using these graphs, we can define one more, we need one more definition. We say that an induced k-comb, if you have a graph G and some induced subgraph isomorphic to one of these structures, we say that such a subgraph is settled in G if there exists a vertex which is adjacent to all vertices of the clique, but not adjacent to any of the vertices in the stable set. And notice that if G is a CIS graph with such an induced comb, then there exists a maximal clique containing the clique part of the comb. There exists a maximal stable set containing the stable set part of the comb, and they must intersect. And the common vertex in the intersection definitely looks like that. So this is a necessary condition, and actually not only for this kind of graphs, but also for their complements. If you look at the complement of such a graph, the clique will turn into a stable set, the stable set will turn into a clique, and in between you have exactly the complementary edges of this perfect matching. So a necessary condition is for the CIS property is that for every k at least 2, whenever you have an induced comb in the graph, both such a comb or the complement of such a comb, if you have it, they must be settled. There must exist a vertex adjacent to all vertices of the clique, but no vertices of the stable set. Now, using this necessary condition, some solved special cases were obtained in the literature. So an interesting conjecture was posed by Vasek Kvatal in the 90s. He conjectured that if you exclude large combs of size 3 or more, and also their complement, so if we assume that the graph does not contain any of those, then it's actually enough for the CIS property that all the induced 2 combs are settled, so the 4 vertex paths. This necessary condition is also sufficient. And so this conjecture was proved independently by Deng, Li, and Zhang, and also by Andrade, Boros, and Gurvic. If you check actually the proofs, you will be either impressed or disappointed, because these proofs are both long and technical. They're different proofs, but they are not simple, neither of them. And this result actually generalizes the work I mentioned before of Grillet on partially ordered sets, because the resulting graphs do not have 3 combs or their complements, but they are even more special. Also, this conjecture and its proof generalize the characterization of comparability graphs, which are CIS, which was obtained also by Zhang in 95 and is related to the result of Grillet. And in fact, the problem of recognizing CIS graphs can be solved efficiently in several graph classes. In comparability graphs, which are the ones arising from partial orders, those that have a transitive orientation. In line graphs, and more generally in claw-free graphs, graphs excluding the induced claw, K13. And we will say a little bit more about the case of C4-free graphs, graphs not having an induced 4-vertex cycle. This result will follow from a characterization of strong cliques in such graphs, which we will explain in a moment, and the fact that C4-free graphs have only polynomially many maximal cliques, which can be generated efficiently. These are known results from the literature. A very recent result is a characterization and in fact a complete classification of diamond-free CIS graphs, which also implies a polynomial time recognition. And we can use some more big results from the literature to observe, for example, that the CIS property can be tested efficiently in graphs of bounded clique width using a meta-theorem of Kursel, Makowski, and Rotix, which says that every property of a graph which can be expressed in certain logic can be solved efficiently on graphs of bounded clique width if we know how to build a graph using the definition of this notion. I will not explain it here, but it's some kind of algebraic construction of a graph with a small number of labels. And there is a result which also we need to use here of Ohm and Seymour, saying that we can actually compute such a construction of the graph with a constant number of labels in polynomial time if we know that there is a constant bound. And finally, just by brute force, we can check the property in graphs where the cliques are of bounded size or the stable sets are of bounded size. These are quite different approaches. So it's really a challenging problem how to recognize CIS graphs, and a unifying approach is still missing, if there is one. But some of these results imply that for every graph F with at most 4 vertices, if F is excluded as induced subgraph, then it can be determined in polynomial time whether a given F-free graph is CIS. From 5, if you exclude the graph on 5 vertices or more, then we already do not know. We have some open cases. Now, let me explain just in a couple of minutes how the idea is for C4-free graphs. So we say that a vertex V in a graph G is simplicial if its closed neighborhood is a clique, and any such clique is said to be simplicial. As we already mentioned, it's an easy exercise to see that every simplicial clique in a graph is strong. But the converse may fail. For example, in the 4 cycle, every edge is a strong clique. There are only 2 maximal stable sets, but it is not a simplicial clique. And in fact, the relationship between simplicial cliques and strong cliques can be also observed as follows. When is a clique not simplicial? It means that it doesn't consist just of a vertex and all its neighbors. This means exactly that every vertex of the clique has a neighbor outside of the clique, which is the same as saying that the neighborhood of the clique dominates the clique. And the clique is not strong if and only if there exists a stable set that dominates the clique. By definition, not strong means that there is a maximal stable set disjoint from it. But if you just focus yourself on the vertices in the stable set which have neighbors in the clique, they must actually dominate. So you see that the red condition implies the blue one. What we will show is that if the graph does not contain any induced 4 cycles, then the converse is also true. The blue condition implies the red one. So if you have a clique in which the neighborhood dominates the clique, then it can be also dominated by a stable set. And in fact, the argument is simple. Let's take such a clique. It is not simplicial. The neighborhood dominates the clique. We will show that it is not strong. So the situation is as follows. We have the clique, we have the neighborhood, and every vertex in the clique has a neighbor outside. Now, because the neighborhood dominates the clique, we actually maybe we do not need all of the neighbors. We can just take a subset, an inclusion minimal subset of the neighborhood which already dominates the clique. Let's call it S, and we forget about the rest. Now, it turns out that because of this minimality, every 2 vertices in this set S must have incomparable neighborhoods in C. Because if, for example, the neighborhood of U in C is a subset of the neighborhood of V in C for different vertices U and V in S, then we do not need U to dominate C. We could just delete it and have a smaller subset which still dominates C. Everything that's dominated by U is also dominated by V. So the situation is more like this for any 2 vertices in S. And for any 2 vertices U and V in S, we can find a private neighbor U prime of U, which is not adjacent to V, and the neighbor V prime of V, which is not adjacent to U. But remember, C is a clique, so U prime and V prime must be adjacent. And also, the graph is C for free, so we cannot have an edge between U and V. And because this argument holds for any pair of vertices in S, S must be stable, a stable set. So we found a stable set dominating C, and so C is not strong. Okay, now just a word on possible similarities with the famous class of perfect graphs. A graph is said to be perfect if the chromatic number is equal to the clique number in all induced subgraphs. And well, here is an example of a graph which does not have this property. It has clique number 2 and chromatic number 3. And a hole in a graph is an induced cycle of length at least 4. Now, Claude Berge made a conjecture, a famous conjecture in the 60s, stating that for every graph G, if neither G nor its complement contains an odd hole, then the graph is perfect. Then the chromatic number and the clique number are the same. This was a very famous conjecture in graph theory, and it produced really a lot of research until it was proved. And its name was then changed from the strong perfect graph conjecture into the strong perfect graph theorem in 2002. The proof was given by Chudnovsky, Robertson, Seymour, and Thomas, and it's a long proof, around 150 pages long. But this important class of graphs shares, at least superficially, some similarities with the class of CIS graphs. In particular, both classes are closed with respect to complementation and substitution. And also, if we look at 2 particular tests, they look similar for a graph. Test whether G contains an odd hole or its complement. Now we know that this is equivalent to perfection. Test whether G contains an induced unsettled comp or its complement. If it does, then the graph is not CIS. But also there are differences. The main difference is probably that the property of perfectness is closed under vertex deletion, and the CIS property is not. This is what makes the CIS property more challenging to understand. But also this property that having all comps and their complement settled is only necessary, not sufficient. There are non-CIS graphs in which all induced comps and their complements are settled. So there are some similarities, but also differences. And we will see another possible similarity in a moment after we explain what is known about vertex transitive case. We have already seen some vertex transitive graphs in this talk. These are graphs such that for any two vertices U and V, there is an automorphism of G mapping one vertex to another. And these two graphs are, for example, vertex transitive. And we say that the graph is well covered if all its maximal stable sets have the same size. Now, in the case of CIS graphs, we have the following characterization. A vertex transitive graph is CIS if and only if it is well covered, so all maximal stable sets have the same size. Its complement is well covered, so all maximal clicks have the same size, and the product of the stability and the click numbers is equal to the number of vertices. And this is, I think, an interesting result because it shows that within vertex transitive graphs, the CIS graphs are indeed special. They attain equality in the inequality which is always true for vertex transitive graphs, that the product of the click and stability numbers is at most the number of vertices. Also, there is another more recent result from this year. Actually, it's a really nice paper on the vertex transitive graphs and their strong clicks. That's by Hudurovic, showing that a vertex transitive graph is CIS if and only if it has a strong click and a strong stable set. So already one strong click and one strong stable sets are enough that all maximal clicks are strong and all maximal stable sets are strong. Now, if you look at this inequality and you reverse it, you get an inequality which is true for perfect graphs. And vertex transitive CIS graphs satisfy it with equality. So they actually share this property of perfect graphs in the vertex transitive case. And motivated by this observation, we asked whether the property could hold for all CIS graphs, that the number of vertices is at most alpha times omega. Well, it turned out a couple of years later that this is not the case in general. It's true for claw-free graphs, and the construction is actually not difficult. You start with a 5-cycle, glue a triangle on each edge to make it CIS, and then perform some substitution with some simple CIS graphs to construct a graph with click and stability number 7, but 50 vertices, more than the product, and the graph is CIS. But one could relax this question to ask whether the class of CIS graphs has the so-called Erdős-Heinel property. We do not require anymore that this product already is at least the number of vertices, but we allow to raise it to some fixed power. So is there a real number R bigger than 1, such that every CIS graph satisfies that the number of vertices is at most the stability times the click number raised to the power R? Or equivalently, is there some positive epsilon such that every n-vertex CIS graph has either a large click, so of size at least n to the epsilon, or a stable set of that size? If you pick a random graph, it will typically have alpha equals to logarithm n, and also omega logarithmic. So the typical random graph will not satisfy this inequality. But for CIS graphs, this is still open. Okay, and finally, I would like to mention very briefly one generalization, which is interesting for the motivation, the one about D graphs. A D graph is a DH colored complete graph. So we have a vertex set V, and all the edges of the complete graph with this vertex set are partitioned into D color classes, E1 up to ED. And we say that such a D graph is CIS if when you choose for every color class, so you have different colors of edges, right? For each color, you choose a maximal stable set in the corresponding graph. And no matter how you do this choice, there will always be a common vertex in all these stable sets. So this is the definition. If D is equal to 2, then you have a graph and its complement, and then you get the original CIS definition. So this is the concept which has applications in game theory, and it could be reduced to the study of the graphs, D equals 2, CIS graphs, if the delta conjecture is true, which was posed by Vladimir Gurvich in his PhD thesis in 1978, which says that in any CIS D graph, you can never have a rainbow triangle. You can never have 3 vertices such that the corresponding 3 edges are colored with different colors. So it's a very easy to state conjecture, but as far as I know, it is still open. And here is just a final slide, a hierarchy of graph classes around CIS graphs, many of which generalize CIS graphs. And there are many open questions still here to understand the relationships between them. Every dotted line is an open question. And also recognition complexity is open for almost all of these. Some of these classes are hereditary. but most of them are not. So that's all for today from me. Thank you very much. Any questions?
Please allow the participants to unmute themselves.
Participants unmute, you know.
Yeah, please allow them. Participants, you can unmute yourself and you can post the question if any.
Please wait. The control is here. Please wait. Martin, by that time, I have a question. Martin, are you able to hear me?
No. He
Yes,
is
yes.
unmuted himself. Yeah.
Oh, okay. How about the product structure of CIS graphs? I mean, the product of CIS graphs is a CIS graph.
In general, I don't think so. Well, it depends. Which product do you have in mind? Maybe the Cartesian product?
Whatever it be, whether Cartesian or tensor or whatever it be. Are there any product?
Well, lexicographic product would be safe because that's related to the substitution operation. The Cartesian product would not be safe. We have seen at the beginning of the talk an example of a graph which is CIS, right? This one here, it's a product of two CIS graphs. But for example, this one already is not CIS, and it's also a Cartesian product of two complete graphs. But I don't think they were systematically investigated yet for the other products. It's an interesting question.
Nice.
Martin, I have got another question. You see, you said there are characterizations available for vertex transitive graphs, isn't it?
Yes, for the vertex transitive, there are two theorems characterizing the CIS condition.
My question is, what about Cayley graphs or regular graphs? Are there any characterization for regular?
Thank you. So first of all, Cayley graphs are special case of vertex transitive graphs. And in fact, the first result which was obtained was for the circulant case, for the graphs which look like that 36 vertex graphs I showed.
Yeah, they are circulant.
They are circulants, right? And for that kind of graphs, the first theorem which was proved in this direction was actually for this kind of graph. The same characterization as we saw for the vertex transitive case was done earlier for the circulant graphs. I don't think there was any work studying these graphs for Cayley graphs of other groups, just in the vertex transitive case. And I believe that Hujdurovic, in his recent paper 2020, has characterized also certain regular graphs, but not much is known. So one remark is that when you bound the maximum degree, if it's constant, then you can test the CIS property because the maximum clicks will also be of bounded size. So there is automatically you get a polynomial time recognition algorithm if the degree is constant. But in general, it's probably quite a difficult question.
Yeah, it's a quite, because most of the Cayley graphs are in several situations, all these properties are enjoyed by certain classes of Cayley graphs. They are claw-free. One could say when it is C4 free and something's there, but how about the converse part with regard to this CIS?
Yes. Yes, I think that the cubic case is understood.
Any consideration for classes from commutative rings? There are a variety of graphs, right, from zero divisor graphs and so on. Are there anything being looked into in this aspect of CIS?
I'm not aware of any such studies.
Now let me.
But I'm also not an expert in that area, so I'm not sure.
Let us ask about the participants. Unmute yourself and you can post a question. I hope that the host has allowed the participants to unmute themselves.
Yeah. You please. Participants can ask directly.
Directly you can post the question now. You can unmute first, and you can do it now. Okay. So, is there any?
Any questions from the participants?
Martin, you can stop presentation. You can come to the view of speakers.
Excuse me?
Please, you can stop your presentation mode.
Yes.
Yeah.
Okay, thank
Any
you very
participants?
much.
Yeah, just a minute. Participants, anybody now? Okay. Hi. Okay, let us thank the speaker for the very nice talk and very recent developments with respect to the class of CAS graphs. Really, we are very much thankful on behalf of the organizers for this night talk. And thank you, participants. Thank you, organizer, for this opportunity.
Thank you very much again. Goodbye.
Yeah, goodbye.
Okay, thank you, Professor Thamizselvam and Martin. The next session starts at 12:15.
Martin, I need some literature with you. Just I will send an email and our best we can
Yes.
talk about anything with regard to Kelly or some other classes of graphs.
Thank you. Thank
I'll
you.
be in touch.
Yes,
Yeah.
we will be in touch.
Yeah.
Okay, next session starts at 12:15. Plenary talk
Yeah.
2 by Professor V. Aravind.
Thank you.
We have a break for about 30 minutes.
Yeah. Thank you.
ഒരു കാര്യം ഉണ്ട് കേട്ടോ. ഈ